are both called hidden Markov model. And not surprisingly, there is a continuous counterpart also in this domain where the latent variables are made continuous. And this is common filter. Okay, it's also called a state space model, and you will see actually a reason why it's called a common filter down the road. So the inference problem in both of these two models which we are going to cover today is actually the same. We are going to try to figure out the conditional probability of the latent variable y given some observations x. Okay, and you can see this the same kind of strategy can go beyond what we've learned so far. With the help of a graphical model kind of intuition, we can build complex models out of the simpler ones. And here I just want to show you two graphs without even talking about how they should be dealt with. This model is called a factorial hidden Markov model, in which I have still a sequence of observations, but my latent states become more complicated. Instead of having one chain of latent states, I have multiple chains. And then there is a master chain here controlling whether this one is controlled by one of these multiple chains in the between. Okay, you can imagine a real story. Okay, for example, imagine that this is the DNA of yours, and these are basically the indicator of where your DNA comes from in terms of one of the many possible ancestors from Africa, from Europe, from Asia, and so on and so forth. And you, of course, don't know in a particular location on your DNA where that piece is coming from, right? So we made it as a latent state. And then this one is a master controller to control where your sequence are sampled from in one of the founding populations. Imagine this is how God is creating modern people, and you can run now a factorial hidden Markov model over that. Right? Very intuitive story. And in here, you can do the same for the state space model. It's called switching common filter. Very intuitive name. This chain is a switching chain controlling, the observation to be generated from, a switching process between all these different latent chains. Okay, you can imagine. Okay, so maybe you are watching at a radar screen. Okay, you are the guy on the in the air control center to direct flights, and on your screen you see trajectories of planes, and this is what you see. But you may see one trajectory, but out there in the airspace there are many planes, and once they enter your radar zone, they are going to create a trace, right? But you don't actually know the trace you see on your screen is coming from which flight. And therefore, you can imagine this is a switcher telling you that this segment comes from the first flight, that segment comes from the second flight, and then switching back to the first flight, and so on and so forth. So it's a very interesting, useful processes. So today we're going to study the building blocks of this, and I have in the assignment some readings about this fancier version, which you can go home and study how they should be used. Okay, that's the roadmap of today's lecture. Okay, without a quick review of what we learned in the last lecture, I really couldn't do anything. So I hope you really bear with me in going through this again. So this is what we learned as the conditional Gaussian manipulation. I give you a joint Gaussian matrix, and then a joint Gaussian distribution with a joint mean and joint covariance matrix. You should be able to now write down right away the marginal of any subvector and the conditional of any subvector given the other subvector, right? So this is a rule you have to remember. Very, very useful. And we will see very often down the road how this trick is played to make a harder problem simpler. The second slice we went over last time is a little bit more challenging. It basically tells you how to invert a matrix. And I hope you still remember this little cyclic rule of manipulating sub-blocks in the matrix to create elements in this inverted matrix. And we're not going to read over that. And at the end of the day, you can have this matrix inversion lemma, which tells you that the Schur complement, which is a particular component block in the inverted matrix, can be expressed as a function of other building blocks. All right, so you may wonder where we see this being used, you will see actually some surprising places this will be very useful. But before I go that, I'm going to show you a few more slices of linear algebraic manipulation. Okay. Just remember this. I don't think it's interesting to read all this through, but you need to know what is the trace of a matrix, sum of the diagonals. What is the trace of, this is also a cyclic permutational rule for trace operation. If you have a trace for a product of 3 matrices, you should be able to cyclically permutate the argument inside the trace and without changing the value. Okay, so that basically tells you a way to sometimes replace or arrange the order of how matrices are multiplied. Derivative of a trace is defined by this. You can prove that this is the case. And in particular, you will find this one useful. Okay, this is a quadratic form that you often see in many of the density functions. In particular, your Gaussian likelihood function has this term, like in the exponent, right? And it is basically a product of 3 things. And using the cyclic rule, we can actually move around this x to here to make it like that. And then using the derivative rule, now we can basically take a derivative of the constant in this term and then get the derivative like that. So again, a very useful trick. Determinant and the derivatives has this relationship. The log of the determinant, if you take the derivative of that, becomes the inverse of that matrix. Okay, so these are the rules I want you to remember, which will be very handy down the road. So now let's study the question. So the first model, which is the counterpart of the discrete mixture model in the continuous space, is this something called a factor analysis. It basically says the following. Suppose that you observed some value y, okay, let's put it in maybe a n-dimensional space, okay. Now you imagine that the y actually comes from some latent space x, okay, and the x may live in a m-dimensional space. Usually, we actually think, M is a smaller dimensional matrix. You have high dimensional observation, and you want to do dimension reduction, to a small dimension. And that's actually what this picture is showing, right? You have this x in here, and it is living in the lower dimensional space, it's a 2-dimensional space, but after this generative process, I'm going to tell in a second, you actually create a y, which is in a 3-dimensional space. Modern machine learning start to turn the whole thing around. Nowadays, you'll see stories like doing the deep network where you have a low-dimensional observation. You want to blow it up into a very high-dimensional space so that you can get whatever features out of it. But mathematically, they give you the same type of problem. Okay, so I'm going to use this very simple example, 2 to 3 space dimensional transformation, to tell you the generative process. So we imagine that x, we first have a latent variable x, which can follow a Gaussian distribution, okay, and it may has a 0 mean and some variance, and we actually it's written here already. It's just a standard normal distribution, and then once x is generated, I'm going to create a y by actually multiplying x with a matrix. This is known as the loading matrix, or actually not A, but the pi matrix, okay. And the lambda matrix, this is called the loading matrix, and it looks like this. It's basically this lambda matrix equals to maybe 2 very skinny vectors, okay? And they basically are the basis of this so-called lower dimensional space. You can kind of view this as, for example, this one and this one. Therefore, what does x mean? Well, x basically represents the coordinate of a latent point in a space defined by this lambda. Okay, so here, for example, this guy, if you look at them in a 3-dimensional space, it has a coordinate of this and that, and maybe a z on this one, right? But in a 2-dimensional space, it has a much simpler coordinate. It has this one and that one to be the coordinate. Okay, so that's a lower dimensional thing, and then you are going to add some noise onto that, okay, and that basically gives you the observed y. So our question is to invert the problem, given the y, how are we going to infer the x? Okay, clear about that question? So, and I'm going to give you a roadmap so that down the road we're going to use the same technique again to make things very easy. Okay, the roadmap is the following. So we have this x, which follows a Gaussian. Okay, and then we also have a y, which is conditioned on x, right? And that's also a Gaussian distribution. Okay, then we can conclude that the joint distribution of x and y should follow what? Yet another Gaussian distribution, right? And if the joint distribution of x and y is a Gaussian, then what about the conditional of y given x? It is also a Gaussian. So we have Gaussian everywhere. What's the catch, from this observation? It means that to define, this distribution, that distribution, this one and that one, all we need is to figure out the mean and the covariance of that distribution. And that completely determines the distribution, right? And now the problem basically boils down to, given the data, like y, how are we going to actually compute the mean and the covariance of a various marginal and the conditional distribution? So here is basically the roadmap. All right, suppose now we actually have the entire data. We have both x and y. Forget about anything being latent yet. Let's just assume they are all there. Then how can we write down the mean and Gaussian of their respective distribution using known information? So we know that x is already following a Gaussian with mean 0. Right? And sigma to be what? To be 1. Right? And if now we think about this line, we say, now this x and y must jointly follow a Gaussian distribution with a big covariance matrix and a big mean. Then we can basically divide the problem into this problem where we fill in each of the blocks one by one. Here we have a mu x, we have a mu y, we have a sigma xx, sigma xy, and a sigma yy, and a sigma yx. Right? That's basically our straightforward goal of writing down the joint distribution. So how should we do that? Well, we first review that rule already. We know that this partial, this mean and the variance of the partial vector is just defined by, as the component in that covariance and in a joint distribution. So we can basically compute them directly. So how can we compute the sample mean from data? Well, just by definition. I will say that we already know that y equals to what? Equals to lambda times x, right? Plus a mu, and plus some noise with a 0 mean, and maybe a covariance of this. Then the expectation of that is what? As I wrote here, it is basically mu itself, right? Therefore, we now have basically mu of y equals to this figured out. Then we compute the sigma y and y. By definition, it is the variance of the y itself, and this is the definition of that. And we bring in mu, which is here, okay? And so this mu is actually due to the fact that the E is defined by y minus its mean, which is already computing here. Therefore, we borrow here to here. And then after some steps of manipulation, you should be able to figure out that the variance of the y is actually lambda times lambda transpose plus psi. Clear about that? So what we achieve? Now we achieved this one being computed, and this one being computed, and that one we know already, right? That one is the variance of the x. It's already defined to be a Gaussian with unit variance, and this one is what? Is 0. So all we need to define compute is this one. So how to compute y sigma of yx? Do you know the definition of that? E of y minus mu y and x minus mu x, right? And then you just do the right thing, basically put basically I think I have something in here already. You can just oh yeah, sorry. One more step here. Y should be replaced by the definition of y in here. Therefore, it is really lambda of x plus mu, and minus mu, and plus something. Anyway, we are going to visit that whole thing later. But let me look at this term first. I will have a few words about that. So this marginal distribution of the y actually follows a Gaussian distribution with mean at mu and with a covariance at here. So this is actually a very interesting thing. So y supposedly is a n-dimensional vector, right? And the lambda, remember, is a skinny vector. We call it a skinny matrix. We call it a vector loading matrix, right? I drew it in the wrong place, so let me change it here, right? So basically, supposedly y should follow, a very big kind of covariance matrix. But this covariance matrix is actually resultant from a summation of these two things. One is a diagonal matrix of n-dimensional. The other is a outer product of two small skinny matrices, which means they are no rank. Okay, and therefore, this is basically an interesting thing. It is not a full covariance matrix. We call them a constrained covariance matrix because the internal structure inside Y, even though it is high dimensional, may actually have a very low dimensional structure specified in here. Okay, and the rest, full rank, the seemingly full rank is made by a diagonal noise matrix, a noise information. Okay, so that's the first thing. So we have the two pieces already, right? We have the marginal of x and the margin of y, and the only missing information to fill in that joint distribution covariance matrix is the covariance between x and y. And here is how you compute it. You just bring in the x and bring in the y, and by definition, y is a function of the x, and after a few more steps, you'll find the covariance of x and y is the lambda itself. Okay. So up to here, now we can just directly write down the joint distribution of x and y like this. Clear about this step? Okay, very, very straightforward. And then what should we do? What is our goal? Our goal was to figure out, given y, what is the posterior of x given y, right? And now we know this already. Do we know how to do that? Right, so we actually set a rule about writing down arbitrary conditional of subvector in a Gaussian given the other subvector, and we just use it, right? So we have these submatrices being all these little different components. We just compute it, and they basically become the large sigma matrix. And then we actually knew that the sub-Gaussian, the mean of the conditional of a subvector is this one, and the variance is this one. So we now have already a good representation of that. Okay, just directly coming from here. Okay, so this is nothing strange by just using the very definition of the conditional Gaussian in our matrix format. Any questions so far? Then what we are going to do is to maybe do something even in addition. So remember, we have this this matrix inversion lemma, which tells you a possible way of even simplifying, symbolically at least, a inversion, in one way or the other. And therefore, there are at least two ways of writing this down, right? And how should we write that? So how about the way, if you look at this one is actually quite similar to this one, right? So how do we see the similarity? If you make, for example, the E inverse to be I, and maybe the F here to be corresponding to the lambda T, and maybe the G here correspond to the lambda itself, okay? And then maybe you can also put H. There is a little H in here, and call H to be the minus of psi. And then, you can pretty much find a one-to-one correspondence from this term to this term, right? It is not quite one-to-one yet because here you have a bracket, an inversion of a matrix. You have an inversion here. It has two terms ahead of it and two terms after that. Here I have one term ahead and after. Well, what's the missing term? If you put the identity here, then the identity actually is what we define to be the E. Then actually gets exactly a mapping from here, right? So with that, now you can actually replace the thing in here to be the thing we're defining here, and then you get to this alternative way of writing down the conditional covariance, which sometimes make people feel happier than the other one because it is just an inversion of a single matrix. Okay, and also there are additional advantages, in here computationally, because in here, remember we have this is a lambda. It's a skinny matrix, right? And skinny outer product by another transform of the skinny matrix is producing a big matrix, low rank but big matrix, and if the real data is a very high dimensional, say you have your real data in 1,000-dimensional space, this is going to be a huge matrix. And then this rule tells you that you have to produce the big matrix first, invert it, then multiply by the transform to push them into a low-dimensional matrix, and then get this covariance. Remember, this covariance is a low-dimensional matrix, right? It is the covariance of X given Y. But to compute that, you need to go through a detour to get high dimensional. But this one is very handy. You directly manipulate in a low dimensional space, right? This phi is what? Is a high matrix, but it is multiplied with the transpose of that skinny matrix. Therefore, the product of these three terms is directly producing a smaller matrix. Right? Therefore, inverting a matrix here only amounts to inverting a m-dimensional matrix, and here you need to invert a n-dimensional matrix. Okay, so that's kind of the virtue of this manipulation, even though they are equivalent. And then accordingly, you can now bring back this to this particular place. By some massaging, you will get again a low dimensional operation to compute the mean, the conditional mean of the latent variable. All right, so that's kind of a simple story. We already finished our inference problem in factor analysis. We know how to compute the latent variable conditioning on the observed variable. That's the results. Okay, and there are a number of interesting observations that you can see from here. First, this posterior covariance, okay, as computed here, it seems to have nothing to do with the data. It's very interesting, right? Somehow the loading matrix and the X, the latent variable itself, contains all the information about the output, but the variance of the input, of the latent input, has nothing to do with the observation. Okay, just by this. And then computing, the mean of the posterior is, it's kind of a linear operation, which is, transforming basically the observed vector into something in the latent space. And this is the transformation matrix. Okay, so geometrically now you can see we can view this true Y, which is in the original space, to be represented by its maybe in the following way. It is a projection X, okay, in the low-dimensional matrix, and this low-dimensional matrix is spanned by a loading matrix of lambda, which is centered at mu. Mu is basically the origin of that low-dimensional matrix. It gets a coordinate like that, and then you get the x. And then to create the actual observed y, it could be beyond this low-dimensional space just by pure reason of noise. So you have a Gaussian noise around that to move it outside of the low-dimensional space. But that move is purely a noise term, which is intrinsic it's not intrinsic to the data. Therefore, when you compute the covariance of x, that particular information is not taken into account. All right. Any question now? So we finished the inference problem. Basically, now from y, we know how to compute the x given y. And this model, of course, right now assume that we know the parameters of the model. So what are the parameters in here? The most important parameter is the loading matrix lambda. We actually don't know that yet, right? And you can argue that this the psi, which is the noise of the signal, after you load the vector, is also unknown, so that will be estimated. So now we need to figure out how to do the estimation. Okay, so any clue how we should do the estimation? Can we begin by some general principle? Given data, we have a probabilistic model, and what kind of estimator is legitimate for? Okay, we want a maximum likelihood of estimation of those coefficients. And okay, that's a good idea, but now look at the graphical model. We basically are in this domain. We have something observed, something unobserved, and so what kind of question it will create in the maximum likelihood estimation? Yeah, so yeah, you have latent variable, without even looking, writing down the problem, just by looking at the graphical model, you already know you're going to face some trouble, right? There are latent variables in here, and in fact, now you can actually write down, the marginal likelihood. In fact, the good thing that we actually have an explicit way of writing down the marginal likelihood of data already, right? We already computed that P of y marginally followed, a Gaussian distribution of mu m and sigma yy, mu y, right? We actually have a closed form of that already, right? Remember, this guy equals to lambda transpose plus psi, something like that. Right? So we can actually write down a closed form expression of the data likelihood already. Okay, it is a function of the parameters, and you can actually directly, seek a estimator of the lambda and psi, which maximize this guy. Why don't we do that? Well, the truth is that it is not very easy to do, because these two things are coupled. Not only coupled, they are coupled in a nonlinear way. They are first summed together, and then they got inverted, and then they actually are further multiplied with s, in which the s contains, the mean of the latent variable. So all these are three parameters we have to estimate got entirely entangled in a nonlinear fashion. So you can imagine, making a estimation in this case can be rather difficult, right? You don't, remember one of the virtue of the Bayesian network is to allow things to factorize, that you can estimate each coefficient independently of others. But in this case, everything gets entangled together. It's a not good idea. And by the same intuition we learned from Bayesian network, we know that if you pretend all data being observed, x and y being both observed, then the complete log likelihood are likely to be factorizable. Right? So now let's give it a try. We put x and y both in place. Then you see this nice little decomposition, where you have this term coming out, and this term still, in here, but at least they are coupled in a linear fashion, right? And with some little arrangement, you basically have this, where phi appeared in two places, but this lambda appeared in only one place, right? All right. So, but here there is a assumption. which is that you have to observe the x, and in our case we didn't, right? And so we've learned EM algorithm. What's the solution to that? We replace the x with their expectation, right? So that we run the EM procedure. And where does the expectation come from? Well, we just actually finished our inference of a p of x given y, right? So we have everything in place. So for that, now we decided to choose the expected complete likelihood to be our target, and we already know a theory to justify its use. It's actually equivalent to the maximum likelihood estimator, and in here we're going to replace our sufficient statistic of the latent variables by their expectation, and therefore we actually had these few terms. Here we have a marginal expectation of a single x, and also the expectation of a product of x. And that exactly corresponds to the mean and the covariance of that latent variable, which we actually knew already, right? So with that, all you need to do is to bring in this and that into our computation, and then you do it iteratively. Given that, you now estimate the lambda and the psi, and then given the lambda psi, you re-estimate these expectations, and iterate until convergence. All right, so that finishes the EM algorithm. In fact, the M step, estimating the psi and the lambda, are still non-trivial, but they are doable. They actually give you some nice closed form computation, which I just showed you here. Okay, for example, here the psi is just the sample covariance, and the loading matrix can be pretty intuitively derived by the product of x and y divided by the variance of x. Okay. Any questions so far? We've done with factor analysis. So imagine if you don't have this Gaussian matrix manipulation trick, and you just do the inference in brute force with two continuous random variable. I couldn't imagine how I should do it. It's going to take you some trouble, to figure out all these equations. But realizing the marginal, the conditional, and the joint being Gaussian makes your life a lot easier. All you need to do is to manipulate the matrix and the blocks in the matrix in some smarter way to put together your estimate. Right. So here, no integration is involved, no marginalization is involved, just a symbolic computation, right? So that you know how this sample mean and the sample covariance can be directly obtained from data. All right, so any questions so far regarding the estimator?
I have a question.
Yes.
So why can you take derivative with respect to phi inverse to get the MLE of phi?
Why can I take a derivative of a phi inverse? Oh, here?
Right.
Oh, I can, I just treat, I'm going to estimate the phi inverse directly. I'm going to, for example, directly estimate the precision of that matrix. Yeah, it's just you can directly worry about estimating the coefficients, but you can also estimate a function of that, and this is just a function of that. Right? And I have to say, doing this makes my life a little bit easier, just convenience, because there is an inverse in here. I don't want to, make it a second order by taking, directly a derivative over that original thing. Any other comments? Good point. Good observation. Okay, so there is one thing I want to raise your attention, which is this. Okay, there is something called degeneracy or identifiability, which some people may not pay enough attention. Okay, if you look at the term actually in the likelihood function, okay, maybe in let's maybe look at more obviously in here, okay, you actually see that the likelihood of data, okay, is actually containing a term where you see a product of the two loading matrix, okay, and similar thing actually also exists in here, even though I didn't express them explicitly, okay. So there is always a question regarding a outer product between two matrices, and then you want to optimize this value. with respect to the matrix itself. Why? Because you can actually imagine that as well, in which this Q matrix is a rotation matrix, which if you multiply Q transpose versus Q, they equal to 1. Okay, so that two thing is equivalent. But on the other hand, you have this part and this part being indistinguishable, right? It means that you may estimate a phi, star, which appear to be optimizing the loss function, but you may also get the estimator to be a pi star multiplied by a q, which actually is achieving the same effect, even though this pi star and the pi star times q are two different matrices. So geometrically, what does it mean? It means the following. If you estimate a loading matrix, as I said, it basically defines the basis of a subspace, right, where the x are supposed to be created. This is a submatrix spanned by these two lambda 1 and the lambda 2. But the same lambda times q will give you the same kind of likelihood of the data, but this rotated version is going to generate a slightly different basis of the original space. Okay. It doesn't really change the game too much if you don't care about interpreting the meaning of the x. For example, your x will be still a point in here, and with this rotation of the axis, the coordinate gets changed. But it doesn't fundamentally change the fact that x is a two-dimensional latent vector, right? And what does that mean? It means that if your goal is to use a factor analysis to achieve a storage advantage or some computational advantage, in that you instead of handling the high-dimensional y, but now you handle the low-dimensional x, you win, okay, by doing this, regardless of what color of the axis you use. But if your goal is to actually seek an interpretation, okay, of the x, for example, nowadays we often use LDA topic models, neural network, and many other techniques to do the so-called dimensionality reduction or dimensionality explosion, basically a projection into latent space, and then starting from there to interpret the projection. I have to say that this is not a very safe practice, because the interpretation can be arbitrary, okay, because this rotation can change the entire meaning of your interpretation. Okay. So that's what people worry about, the degeneracy identifiability. We say that the lambda is not identifiable up to a rotational difference. Okay. And this is a cautionary bit. I want you to at least be aware, so that if some people run you a factor analysis and tells you actually axis 1 corresponds to the topic of politics, the axis 2 corresponds to the topic of sports, you want to say, how about I rotate it? And can you actually tell them apart? And you probably can somehow discourage your user from seeking that interpretation. Okay. All right. Clear about factor analysis? Good. Now what's next? Okay, what's next? I think I have exactly half an hour left for telling you about Kalman filter, the space-based model, which are supposed to take multiple lectures. But let's give it a try. Okay, I'm not sure I can do it, but let's see whether I can finish it. So it is a model that is extremely interesting, actually, in the literature, and you probably heard our story already. So here is the model. It is just a collection of factor analyzers, in the time domain, so that at every time point, I have a different factor analysis operation. But all these different time factor analysis are using the same loading matrix. They are living in maybe the same lower dimensional space, but the point themselves, actually is evolving. So you have a transition matrix here to govern how in the latent space the points are moving, okay, across time. across space. And then at every time point, you have an emission function, y, generating your signal from the latent to the observation. And in here, we call the loading matrix C. Remember, in the previous factor analysis, we called the loading matrix A. In here, everything changed. The A gets in here, and the C is in here. Okay, and then we have a number of very simple noise model. So here, W is the noise. Okay, the noise also gets a transformation. Okay, and here, the observation also gets a noise function, and it's a zero mean R covariant noise Gaussian distribution. Again, here we don't make assumptions on the R and on the Q. They may be a full rank matrix. Could be a diagonal matrix, but at this point, we want to make it fully general. And then you have the starting point to be a almost standard Gaussian matrix. Okay, and of course, in general, you can make them more flexible by turning this transformation function to be an arbitrary function. But we can talk about it later if we have more time. Yeah.
All of those yt should depend on xt, right? Not on xt minus.
What's that?
The yt should depend on xt and not xt minus.
Oh, okay. Good point. Yes, it should depend on x. Good catch. Okay. Any other things? Oh, okay. Second one. Yes. Thanks for the very, very sharp eye. Nice. Okay, let's move on. So, and here I'm going to inspire you with another example, which is going the other way around. I want you to see something other than just the traditional way of using factor analysis. In here, let's do an aerospace or dynamic control kind of operation where we are not doing the dimensionality reduction. We just want to seek a latent space inference. And this is a very latent space inference problem. You observe a point that is moving in space, in two-dimensional space. Therefore, you have the two coordinates. Okay? And you imagine that this whole thing is like the y's is caused by some true trajectory, okay, which is moving from certain position and also with a certain velocity. Okay, we can actually know in our latent space, we know the whole story. We know not only the location of x and also the velocity of the x. Okay, and how to generate this the observation from this latent information? Well, Newton's law, very, very easy, right? The next step is going to be the first step times the velocity and the unit of time. Okay, so this is basically a generative process. You have the transition matrix A in here, and you have the loading matrix in here. Okay, and then our problem is what? Is the following problem. We have at least two inference problems that are very interesting. One is called the so-called filtering problem. I'm going to give you a sequence up to t. Okay, then I want you to estimate the latent position, okay, at time point t. Okay, so like this, I'm going to just see a longer and longer observation sequence, and each time I'm going to ask the value of that. Basically, it's about now you see the whole signal and its a historical trajectory. Where is the plane in the airspace? That's basically the problem, right? And this problem is equivalent. It's a Gaussian analog to the so-called forward algorithm in our HMM, because you actually can enjoy this recursive definition as we had before in the forward-backward algorithm. Remember the forward signal is nothing but a conditional distribution of the latent state given the partial sequence, right? And that one is recursively defined by this, which is the alpha message is proportional to the observation, the emission function times transition times the previous signal, right? Okay, but unfortunately, this type of functions are not now a tabular function. Remember, originally we have the tabular function, and here they are all linear Gaussian distributions, and we need to figure out how to compute this, right? The second question is about smoothing. it's really about asking a slightly more kind of estimation with regret or something like that. I give you the whole sequence. Before we basically say, I see this whole sequence already. I ask you the latent state right here. But let's imagine that now you've done with your daily work and you want to report to the manager, what's happening in today. It is kind of silly not to use the information after that to report, to do a re-estimation, do correction of the position in here, right? Originally, you can make the prediction in here just based on information up to here, but now you'll see more information after that. Do you think it will be influencing the way you estimate this? Of course it will, right? So that's basically equivalent to the so-called, like the backward algorithm or the forward backward algorithm in HMM. You basically want the information to pass back and redo this estimation. And you can do this for any place in the entire sequence. And here is the backward message. So these are the two inference problems in what we call the state space model. And the common filter is one of these algorithms that help to solve the first inference problem, the filtering problem. Okay. And you can actually see the effect of these two type of inference problem already. So here is a plot showing you a kind of a generative story of the model I just showed before, okay, where you see a two-dimensional trajectory. You want to estimate their true position, but the model actually contains the the velocity and the noise. And here is actually a running trace of the experiment. You have the true data. This is your observed position of the trajectory, this square thing. Okay, and then you run the filter. You basically use the sequence up to now to estimate its position. You get such an estimation, okay? And this actually are the true position, okay? The observed are actually the one with the stars. And now your kind of sequence of Gaussian kind of ellipsoids and their center, which is connected by the dotted line, is the estimate trajectory. You can see this estimated one are kind of getting okay with the true one, but not quite right yet, right? But now if you do the smoothing, like use the whole sequence to go back and correct the estimation, you get a much better estimation of the trajectory. Okay, so that's basically one utility of this type of model. And some now I think in electrical engineering and in psychology, people really take common filter very seriously, and many believe that this is actually happening in our human brain when we actually observe stuff. For example, I observe you guys here. You can imagine I'm nearsighted or I have some kind of, I'm not a perfect recorder. So you may be in that position, but what I perceived could be 1 centimeter offset of that exact position, my estimate, right? So basically that creates the two images. You have the real X, okay, which is in maybe a three-dimensional space, and I have a Y on my retina, which is a kind of a perceived position of you, and that is living in a two-dimensional space. And in my brain, okay, I have to use that two-dimensional information to recreate a three-dimensional thing to estimate where you are, even though my retina is a two-dimensional thing, right? And that's basically regeneration of the three-dimensional information. And what you get is that, you get information of y up to t, and you also estimate your x information up to t, and now you see a new observation t plus 1, and how are you going to predict this one? Right, so that's pretty much what a common filter is doing, and this is what I believe to be what you are doing in your driving or other moving experience. You need to kind of intuitively estimate where your car will be heading, before you actually step up your gas. Otherwise, you will be miscalculate and run into someone. Right? All right. So now let's do some non-trivial, maybe even dazzling exercise to figure out how to derive the equations for common filter. to make sure that I don't make mistake myself, I have my cheat sheet here as well. So in case I lose track, I'm going to follow that. So again, the key information here is that we have a common filter like this, and we should now realize that everything in this model is nothing but Gaussian. Okay, you emit information based on conditional Gaussian. You transition to the next state also with a Gaussian distribution. Therefore, you should be safe to assume that everything, being a conditional of some subvector given others, or a marginal of that subvector itself should be a Gaussian distribution, right? Therefore, for example, estimating this, which is the latent state given a partial sequence, must be also a Gaussian distribution. Therefore, all we need to estimate are, their mean and the covariance, right? So, in a sense, we're going to define two terms. We want to define x of expectation of xt given y1 to t. We want to give it a name, okay? We want to call it a mu of 1t, okay? This is the conditional mean of my latent state. And then we want to have a this is the covariance of that conditional estimation, and we call it p of 1 to t. This 1 to t is important. It basically tells you where the information that is conditioned on is drawn from. Okay, so the whole inference problem boils down to estimating these two things. Once you have this estimated, you are done. So now the problem comes to how do we estimate that? It's breaking down now into two steps. Okay, so common filter go like this. First, it is going to make use of something called a prediction step. Okay, so that you can calculate p of x t plus 1. Okay, given y1 to t. Okay, from our earlier xt and y1 to t. Okay, so that's the first step. This is a prediction. I'm going to move one step forward based on the sequence prior to my current time step. Okay, and this is sometimes called a time as update. So this is a pure prediction step. Okay, and then I'm going to update that by introducing a new piece of evidence. Okay, so that you can actually get this part even further to this part by integrating this information with an additional piece of information from the data. Actually, this is additional information from the data. You have seen one more observations. Okay, and you will see the reason why we break them into two pieces, because that allows us to quite clearly manipulate various joint Gaussian distribution. Okay, all right. So now let's look at maybe the high-level picture. Okay, so the high-level idea that I'm going to introduce to you so that you can remember is always this idea. So we are going to deal with basically two Gaussian vectors, okay, and they can be, right now I've been kind of agnostic about where they are exactly, but just imagine there are two subvectors, each is a Gaussian and jointly is a Gaussian. Therefore, they should follow basically mu1, mu2, and sigma 1, 1, 1, 2, 2, 1, and 2, 2. That's basically our main vehicle. Okay, so what we're going to do is to do the following. Every time we start from a piece of that, say Z1, okay, and then we're going to get Z1 and 2 together based on some kind of a process that allow 2 to be generated from 1. Okay, therefore we start to get their marginal, their conditional, and then with this joint, we can basically start working on the Z2 given Z1 or the Z2 itself. That's kind of the general idea. Okay. And now if, for example, we let the Z1 to be, say, xt, suppose we are dealing with this task. Okay. And then what we have could be the following. So we can basically say we have originally, xt and y1 to t. Okay, that's our original starting point. We finished up to here, my entire estimation. Okay, and now I'm going to basically generate p of xt plus 1 given y1 to t. Right, so that's the next information. Right, and this takes what? This basically needs only a transition function, which is this in general, and we said that it can be a linear function a of xt plus a noise w. Right, so that step basically is what makes this happen. And then we're going to now actually introduce a new piece where here you have what? A new observation at yt plus 1, right? Of xt plus 1 given, right? And you know this function already, right? So this is because y equals to cx plus v, something like that. And with that, what you can do is to create now what? A xt plus 1 and yt plus 1, right? Conditioning on y1 to t. You basically create a joint. Okay, it is a conditional joint. It is a joint of two variables, then conditioning on all the rest of the observations, right? And once you are there, you can do one more step to just follow this idea to now invert the problem to make only one of the subvectors to be conditioned. So that gives you y, okay, y1 to t plus 1. All right, so this is kind of an entire exercise. How do you bring more information into there? It's kind of an indirect way. You bring information by making them a joint, and then you manipulate the conditional to somehow fold the new information into the right-hand side of the conditional distribution. Okay. So with that, you pretty much have the whole picture already, and let's do a real operation. Okay. So let's talk about the dynamic model. Let's do time update first. Okay. So time update means that now you need to compute basically the e of xt plus 1 given what? 1 to t, right? Yeah, let's do it together. I mean, this is help you to. And then what's the next step? It should be a function of xt, right? So we have now, a of xt plus maybe I don't know, I forgot. It's a g of w, I think, t, right? Okay, and what does this correspond equal to? Equals to a, and our old definition of the conditional mean, which is a mu of 1t, right? And plus what? Plus 0, right? Okay, so this one basically by definition equals to, okay, the mean of the latent variable at time t step 1. But conditioning on what? Actually, I should be careful in here. I think I wrote something wrong already. What did I write wrong? Right? That part is actually I should be more careful. Let me do this. it should be now t plus 1 given t. It is the mean of the x at time t plus 1 step given observation up to t. Okay. Okay, now let's compute the expectation of the sample the covariance minus this guy. Okay, and so then you know the mass. We need to bring in a xt and plus gw minus x hat t plus 1 t, and same thing here. Sorry. Okay. And you can pretty much take out, I guess, the t, the a, and bring in the expectation to be in here, which is xt minus see that step? Okay. So this is basically taking the fact that this one equals to 0 if you take expectation. Therefore, you can neglect that part. And then you can take this. And this is a constant, by the way, so therefore it doesn't get the influence. Okay. So at the end of the day, what you have is now a of actually I need to I have a few terms forgot. I think I have Q actually is the covariance of the W. Okay, if they multiply together, they have to have a non-zero estimation. Okay, so that's pretty much how you can algebraically compute the conditional mean and the conditional covariance matrix. All right, so well, you can do the same for this, right? Y t plus 1 and the given t and sigma y t plus 1 given t, right? So basically just using the definition of x transition and the y emission to define their conditional mean and Gaussian. And then at the end of the day, what you have is basically this, right? You now have a joint distribution of xt plus 1 and yt plus 1 given y1 up to t. And it is basically following a Gaussian with a long mean vector and a long covariance block, a matrix. And here you basically let this goes to here, and that goes to here, and so on. Okay. Okay, so I think I actually have the exact derivations written like this. So with that, now it's becoming clear, right? We have now the joint expressed in this closed form. And we just use, again, the definition of conditional Gaussian, which has this very handy form of conditional mean and conditional covariance to actually put the proper term into here. And then you actually will get what? Get a p of xt plus 1 conditionally on y. Okay. So what do we have? This is the final function. This is obtained just by exactly, bringing all these terms into, this one. Okay. And that's common filter. Okay. You can see the structure of the common filter. this update, the next state, is based on a predictive state. This one is a state predicted from the previous sequence up to t, then plus a term which we called a common gain, okay, which is to kind of calibrate or adjust the observed y versus the predicted y from your predicted position, okay, and then multiplied by a common kind of a correction. Kind of makes sense, right? Your final prediction is, your final estimation of the next state is the predictive next state plus a corrected version from the observation, right? All right, and this is the definition of this common gain matrix. And the good thing about here is that this K matrix can be pre-computed because it has nothing to do with the data. Okay, so you can pretty much pre-compute this, and then you can run this at every time point you observe a new sequence. Okay, so that's basically what we call a time update and the measurement update, these two terms. Okay, time update does not need common filtering, but then measurement update, when you incorporate the observation, you need a common filter to do that. All right, so that's basically common filter, very, very kind of straightforward in this case by playing with the Gaussian matrix manipulation. And maybe in the simplest case, let's just run the whole experiment in one-dimensional observations to see kind of the effect of the common filter can expose. So suppose you have the points, that is a one-dimensional particle moving kind of in a semi-random fashion, and you have all this transition and the emission matrix, okay? And now you can compute the common equation to be like this. It's kind of a very simple combinations of various variance, of the corresponding random variables. And then you can see actually how the next mean and the next covariance matrix behave, okay, as a function of the different sources of information. The different sources are sources from the time updates and from the measurement updates, okay. So here actually give you already an example. I mean, I'm not going to explain all this equation, but you can see actually the resultant density curves from these two type of updates. So we started from here. This is basically the value of my x, okay, in the current place, okay. And then, the next step, as I just mentioned, come from two sources. One is the prediction based on basically this transition function, and the other is based on the observation I'm going to see in the next step, right? So the prediction actually now can be computed from these equations to be a Gaussian distribution of this shape. So what does it mean? It means that now I have my current estimation of x based on all the data I collect up to now. Okay, it is very nicely estimated, but I'm going to use this to make a prediction of where I am in the next time step. Well, by definition, if I make a prediction, my confidence will be less certain as where I am now. Therefore, the variance will be increased, right? So you get a bigger Gaussian, and interestingly, because we have a kind of a strange noise model, the noise actually gets a 0. Therefore, my predicted position, the mean of the prediction will be the same as my current mean. Basically, I'm predicting I'm not moving, but I'm not certain about where I am now. Right? Therefore, the next Gaussian will be superimposed with the current one with the same mean, but with a bigger spread. Okay, now I see a new data coming in, which might be here. Like the z is actually in this position. Okay, it's set 2.5. This is my new observation. Okay, that basically gets you extra information to move this density function around to here. That gives you a new kind of posterior distribution of my x, which is not only thinner, but also the position gets moved. Okay, so that's kind of the two steps. You have a time update and a measurement update, which helps you to change the variance, accumulate more information, and re-estimate the mean and the variance. All right, so that's basically what I said. The common filter has this innovation, called common innovation, which is how to deal with additional observation and combine them with the current estimation of the latent position. Okay. And here are some insights about how to trade off. Different source of information. If your emission function is rather kind of random, you have a big variance in your emission function, then you should trust your update less, right? If your transition function in the latent space is very stringent, you are having a high confidence on your transition, then you should trust your prediction more than the data. But vice versa, if you have the other configuration, you should try readjust the contribution of the information. All right, and I think this is my last slides I intend to cover today. The complexity of the common filter is not a small one, okay? Because you need to compute this transitional function. Okay, this is the new variance as a function of the old variance, and it requires you to do the n-squared complexity matrix computation. And here, n is the dimension of the latent space. And furthermore, if you want to compute the common game, it is even a more complex computation because you need to invert the matrix, and therefore you have a cubic complexity to the dimension of the observations. Okay, and that's why actually the open problem nowadays is that people cannot run common filter in a very high dimensional space. If you are tracking, for example, 1,000 aircraft, okay, you simply cannot put them together as a joint kind of distribution over 1,000. You probably need to assume they are completely independent, and you track each of them one by one rather than jointly. Okay, but what if you have 1,000 monitors on a single aircraft? You still need to assume them to be independent or partially independent to break them into smaller pieces, and each of them has their own common filter. You simply cannot take the fact that all these monitors are on the same aircraft. They should be running a single common filter, and that thing doesn't happen yet. So, Boeing has been experiencing this problem a lot, and they still haven't figured out how to do it. So you guys can think about, maybe a fancy ways of dealing with even this very old model in a large scale. Okay, so I'm going to gloss over the smoothing problem, which is just the old kind of analogy between the backward algorithm and the forward algorithm, and there is a new name for that. It is called the Rausch-Shriver algorithm. Basically, same kind of matrix manipulation. You get the backward actually inference taking place, and I will leave that for your kind of after class reading. I have some additional, interesting. Okay, yeah, this is another slide. Looking how to learn common filter, the transition matrix. Well, this is the same as what we do in HMM, right? In there, you have the Baum-Welsh algorithm, which is an EM algorithm. You just estimate the latent state, and now with the forward algorithm, which is a common, and the backward algorithm, which is RTS, you now can estimate the expectations of all these latent states. Right, and then you have the learning algorithm automatically in place. Okay, I think there are some additional kind of small, stories, and I'm going to leave it for your after-class reading. Basically, when you see a nonlinear function, you do a Taylor series expansion to take the first term and keep it linear. That's kind of a common trick that we always use. Extend it. Yeah, there's nothing really interesting now. Okay, I think that's the end of today's class. Oh, by the way, so we're going to have a class this Friday instead of next Wednesday. So make sure that there is a change in the schedule, okay?